All right, guys, welcome back. Last IMF that we're going to be talking about, and that's hydrogen bonding. Hydrogen bonding occurs in polar molecules containing hydrogen atoms that are bonded directly to either fluorine, oxygen, or nitrogen. So it has to be a hydrogen molecule or hydrogen atom bonded directly to fluorine, oxygen, or nitrogen for it to be considered a hydrogen bond. So examples are NH3, HF, or H2O. That is a hydrogen atom bonded directly to either a fluorine, an oxygen, or a nitrogen. These are essentially super dipole forces. They're stronger than the dipole-dipole forces. And the reason why is because there's a really large electronegativity difference between hydrogen, fluorine, oxygen, and nitrogen. So it creates this super tight bond, and their relative difference in sizes makes them, like the relative largeness to smallest comparison, makes them able to get very, very close together and create a very, very strong bond. So let's take a look. So if I look at hydrogen and fluorine bonded together, hydrogen is slightly positive, fluorine is slightly negative because fluorine has a higher electronegativity. So I'm already creating sort of a dipole moment here. But this bond that exists between this fluorine and this hydrogen, that's a hydrogen bond, right? Or this force that's existing between this fluorine and the hydrogen, this is a hydrogen bond. So wherever that slightly negative side is, it's going to bond together with the positive side, the slightly positive side. This is a very strong attraction. The hydrogen bond is the strongest attraction that we're talking about in intermolecular forces. And you can see that continuing to go together. So let's take a look. So hydrogen bonds are strong intermolecular forces, which means the hydrogen bond trumps the dipole bond, and it trumps the London dispersion force. So this is going to give molecules that have hydrogen bonds the highest melting and boiling points, higher than what you would predict based on their molar mass. So if I look at methanol and ethane, so remember it has to be either something that is bonded with fluorine, oxygen, or nitrogen. So in this case, we see a hydrogen bonded to an oxygen. So this one is going to have the hydrogen bond. This does not have a hydrogen bond. This is a hydrogen, yes, bonded to a carbon, but remember it has to be a nitrogen, an oxygen, or fluorine. So this doesn't work. So this one is going to have the hydrogen bonds present, which are the strongest ones, which means it should have the increased boiling point or the higher melting and boiling point, which we do see in this comparison. Notice their molar masses, again, are almost the exact same. But again, this one has a hydrogen bond in it, so it's going to have those higher melting and boiling points. Okay, let me show you guys an example. So one of these compounds is liquid at room temperature. Which one and why? So for this one, we've got carbon bonded to oxygen and hydrogen. So we've got carbon bonded to hydrogen and oxygen, here we've got carbon bonded to fluorine and hydrogen, and then here we've got oxygen bonded to hydrogen. So in this case, if we looked first, the first thing we would look at is what are their relative molar masses. So they all actually have really similar relative molar masses, so we can't really base anything off of this. The next thing we would look at is the polarity. All of these molecules are polar, and that means they all have dipole-dipole forces. So we can't base our answer off this. By the way, when it says is it liquid at room temperature, that means it's going to have a high boiling point and a high melting point. So we're looking at something that has the strongest type of bond present. So all three of these compounds are polar, so they all have dipole-dipole forces, which means they all have London dispersion forces, and they all have similar molar masses. So right now there's nothing we can really use to differentiate these. Now, letter C, this is actually hydrogen peroxide, contains a hydrogen directly bonded to an oxygen. And this creates this hydrogen bond. Now, we don't see, even though we have hydrogen and fluorine both present in here, we don't see the hydrogen directly bonded to the fluorine. Same thing here. Even though we have hydrogen and oxygen present, we don't see the hydrogen directly bonded to the oxygen. So this bond is actually the strongest. This is the only actual hydrogen bond that's present, which means this one must have the highest boiling point and melting point, which means this one must be liquid at room temperature. So we'd say that letter C is their answer here. Okay, you're going to do one yourself. Which one has the higher boiling point, HF or HCl? Go ahead and pause, complete the U-try. Make sure you do it on a separate piece of paper and submit it to Canvas. Okay, here we go. So which one has the higher boiling point, HF or HCl? In this case, here is HF, H bonded to F. This is a hydrogen bond because it is an H directly bonded to a fluorine. This is going to have a slightly positive. This one's going to be slightly negative. Here's the relative molar mass. Now look at this one, HCl. Of course, there's a dipole moment that exists here, but look at the relative molar mass of this one. It's insanely higher. So if we were to guess which one had the higher boiling point, we would say this one, which has the higher molar mass. But because this has a hydrogen bond, even though the molar mass of this one is higher, we would still say that this one has the higher boiling point because of the hydrogen bond that's present. So HF is actually your answer here. Okay, guys, that's all I have for you. We'll go over this more in class, but if you have questions, let me know, and I'd be happy to help you out. Thanks.